Hello, my name is Joe Brannon. I'm a distance education student at NC State University taking Dr. Buckner's Design of Electromechanical Systems class. This is the demonstration project. Today I will be demonstrating a magnetic solenoid linear actuator with position control. Let's get started. This is the completed linear actuator. It is made up of three main parts: the actuator shaft, the actuator body, and a length of 24 gauge magnet wire wrapped around the actuator body, creating a solenoid. Recall that when a current is applied to a solenoid, it creates a strong magnetic field inside the solenoid. This field can be used to control the position of the actuator shaft by attaching a permanent magnet to one end of the shaft and a spring to the other end of the shaft. The force on the permanent magnet can be calculated using a finite element analysis tool such as FEMM. Let's take a look at some of the analysis done on this actuator. Here you can see the FEMM model of the solenoid. You can see the permanent magnet down at the bottom with much of the flux going through it. The solenoid would be the outermost rectangle you can see there. Here it is modeled with approximately 1500 turns and 1 amp going through it. A MATLAB script was created to move the magnet up through the solenoid bit by bit in increments of 0.5 millimeters and calculate the force at each point. And here we see the force on the permanent magnet as a function of position in the solenoid. 0 here would be at the bottom of the solenoid as shown in the picture before. A positive force would be pointing up in the picture before, and a negative force would be pointing down. As you can see, there is a strong positive force in the first 15 millimeters of the solenoid, and then it weakens as the magnet gets towards the center. And then as the magnet goes all the way through the solenoid, a force tries to pull it back towards the center as it reaches the end. Now that we know the force applied on the magnet across the entire length of the solenoid, let's use that to our advantage in combination with the spring to control position. We know that when the magnet is at the one end of the solenoid, it will experience a strong force pushing it towards the center of the solenoid. This will move the magnets and the shaft to the right. Now, the spring will be pressed up against the other end of the actuator body. This will cause the spring to compress and impart a force to the left, counteracting the force from the magnets. The actuator shaft will move until the force from the magnets will equal the force from the spring, creating its new equilibrium position. So let's demonstrate this by placing the actuator shaft inside the body of the actuator and applying a voltage and therefore a current to the solenoid. So as you can see, as I start to apply more and more current to the solenoid, the actuator shaft will move left and right, controlled by the amperage applied to it. Now let me adjust the camera so you can get a better view of this. Okay, I've put the camera on a tripod directly above the solenoid and moved the actuator to line up with this 3 centimeter mark on the ruler so it is easier for you to see the motion in the actuator. As I begin cycling the voltage and amperage up and down on the solenoid, you can see again the motion in the actuator shaft. There isn't too much motion here, but this makes sense from the charts earlier where you could see that only about 15 millimeters of the solenoid create a large force on the magnet. The small motion can also be attributed to the large spring constant of the spring itself, and you can get more motion by lowering the spring constant. Other ways in a more industrial setting to increase the usefulness of this actuator would be to add linear bearings to the shaft to reduce the friction between the shaft and the body itself, which is causing some of the jerkiness you can see here. But overall, for a 3D printed linear actuator, this is performing very well. This concludes my presentation. Have a nice day.